Hello everyone, welcome to IIT and Gate classes. This is your lecture 6 on TOC, and in this lecture we are going to start the 8th topic according to syllabus of your second chapter, that is finite automata and regular languages. If you have not seen the syllabus of second chapter, then please watch my second video on TOC. In that video, in the starting itself, I have explained the syllabus of second chapter, and according to that syllabus, or you can say according to that sequence, I am saying that we are going to start the 8th topic. Okay, that is the Chomsky hierarchy. Okay, so Noam Chomsky was the scientist who divided the grammars into 4 categories. Okay, that is type 0, type 1, type 2, and type 3. If you do not have any idea about what are grammars and so on, so you can watch my previous lecture, that was lecture 5. In the lecture 5 itself, in the end, I have explained the topic grammar. Okay, it was the 7th topic according to second chapter of your TOC. Okay, okay, so there are 4 categories of grammar, that is type 0, type 1, type 2, type 3. So this is the Venn diagram explaining the relationship between them. So every type 3 is type 2, every type 2 is type 1, every type 1 is type 0, but every type 0 is not type 1, every type 1 is not type 2, and so on. Okay, you can note it down. Okay, so let's start them category by category. So the type 0 grammar is also known as unrestricted or universal grammar. Okay, so LHS implies RHS. This is the way we define the production rule of grammars now. LHS implies RHS. So in LHS we should have at least one non-terminal, and along with non-terminal we can have any number of terminal or some more non-terminals and so on. So see the line carefully, at least one non-terminal. Okay, we need at least one non-terminal, and in RHS we can have anything. Okay, so let me give you some examples. Like I say S implies AS. This is type 0. ASA implies A. This is also type 0. A implies A. This is also type 0. A implies A. This is not type 0. Why? Because in LHS there should be at least one non-terminal, but here we do not have any non-terminal. Here we have at least one non-terminal, here also at least one non-terminal, here also at least one non-terminal. So all these are correct. Similarly, if I write A, okay, let me do it properly. A S A B small c small d implies say A B C D. Yes, this is also a valid production rule for, you can say, type 0 grammar. Okay, so the only thing which you need to remember is in LHS just see one non-terminal is present or not. If at least one non-terminal is present in LHS, then we will directly say that grammar, yeah, you can say production rule follows type 0 property. Okay, I hope I have made the point clear to all of you. Okay, and let me give you just one more example so that the things get clarified to all of you. See, can I say A B C D implies A B? Is this type 0? That simply say, see the left hand side there should be at least one non-terminal, but here we do not have any non-terminal, hence it is not type 0. Okay, directly say this thing. So this is not type 0. Okay, so why you think that this is restriction that at least one non-terminal? Because non-terminal can produce, see the fundamental definition of grammars, 4 tuple na, NTPS or VTPS. So we say that non-terminal can produce other non-terminal, or you can say terminal also, right? So non-terminal can produce other non-terminal as well as terminals. So if we do not have any non-terminal in LHS, then how we are producing something else? So here directly indirectly I am saying that these 4 terminals are producing these 2 terminals. This is never possible because terminals are the fundamental or basic symbols, or you can say these are atomic in nature. They cannot be further subdivided and they cannot produce anything. Okay, but here only terminals are producing something. This is not allowed. So this is not type 0. Okay, so I hope you have I have made the point clear to all of you. That is, at least one non-terminal must be present. If at least one non-terminal is not present, that means there is no non-terminal in LHS. Then directly indirectly we want to say that terminals are producing other terminals, which is not allowed. Okay, I hope I have made the point clear. Now let's move to the next, that is type 1. See, type 1 is also known as length increasing. Okay, type 1 is also known as length increasing or context sensitive grammars. length increasing or context sensitive grammar. So here we have two conditions. The first condition is grammar must be type 0. See, in each and every type of grammar, we will say like this only. That means in type 3, we will say it should be type 2. In type 2, we will say it should be type 1. In type 1, we are saying that it should be type 0 and so on. See the Venn diagram. Okay, you will get the more clarity. Every type 3 is type 2, every type 3 is type 1 and so on. So in the definition of type 3, in the definition of type 3, I will say that it must be type 2. In the definition of type 2, I will say it must be type 1. In the definition of type 1, I will say it should be in type 0 and so on. Okay. So we are in type 1 now. So I'm saying that it should be in type 0. Okay, now and one extra condition. One extra condition here is LHS implies RHS now. So length of LHS must be less than or equal to length of RHS. See, this is the only restriction in type 1. Okay, so please remember this thing. LHS must be less than or equal to RHS. In type 0, there was no restriction on length. Huh? See here, there was no restriction on length. Okay, I was not talking about length. I was just talking about LHS, at least one non-terminal. That is your type 0. Type 0 is also known as universal grammar, because if at least one non-terminal condition is not fulfilled, then it should not be a production rule of any grammar. That means this is never possible. Now, terminals are producing terminals. This is never possible. Okay, so fundamental definition is not followed here. So hence it should not be the grammar. Hence we are calling it as universal grammar. And why we are calling it as unrestricted? Because there is no restriction at all. There is only one restriction, and that is the fundamental restriction, that is at least one non-terminal. Okay, I hope I have made the point clear. Now type 1 is known as length increasing or context sensitive. Length increasing means what? As length of LHS that should be less than or equal to length of RHS. So let me give you some examples. Like I say AS implies AAB. This is correct. Length, see the length 2, here length 3. We are not concerned about number of terminals or non-terminals. We are just concerned about length. Okay, now if I say AAB implies ABCD, yes, this is also correct. See the length here, length 3, length 4. Okay, if I say AA implies AB, this is also correct. Okay, A implies B, this is also correct. Length are equal. A implies AB, this is also correct. Okay, and if I say AB implies ABCD, you will say that length here is 4, length here is 2, so this is type 1, but no, this is not even type 0. Okay, because here we have we do not have at least one non-terminal, so this is not type 0. Since this is not type 0, then how it can be type 1? Please remember this thing. Okay, let me give you one more example. Let me use a different color. If I say A implies null, what do you think? Is it type 1? No, this is not type 1. Why? Because here length is 1 and here length is 0. I have already told this is null. Null means what? Nothing. Nothing means what? Absence of any terminal symbol. That means its length is 0. This is null string now. Okay, so its length is 0. So please remember this thing. Here length is 0, here length is 1. So this is not allowed. So null productions. These are known as null productions. So null productions are not allowed in type 1. Okay, please write this thing. Null productions are not allowed in type 1. Null productions are not allowed in type 1. Okay, I hope I have made the point clear to all of you. So please remember this fact. Okay, now why we are saying it as context sensitive grammar? Why we are calling it as context sensitive? Let me give you one example. Okay, let me give you one example. See, what exactly is context? See, I am saying like this: alpha A beta implies alpha gamma beta. So A is changed to gamma in presence of this alpha and beta. So here alpha is known as left context and beta is known as right context. Okay, alpha A beta implies alpha gamma beta. So A is changed to gamma. Okay, A is changed to gamma in presence of alpha and beta. So alpha is known as left context and beta is known as right context. Okay, so these are not changing. Please remember this thing. Alpha is not changing, beta is not changing, A is changing to gamma. Okay, now the next question arises: what are these alpha, beta, and gamma? A is non-terminal. You can easily guess this is a non-terminal A. What are alpha, beta, and gamma? These are any combination of terminal as well as non-terminal. Okay, so alpha, beta, gamma can be anything. can be any combination. Properly we should write any combination of terminal and non-terminal. Okay, so let me give you some example. If I say AAB implies ACB, so what will you say? A is changed to C in presence of this A and B. Okay, so here A is left context and B is right context. Okay, similarly, if I say AA implies AD, then what will you say? So A is changed to D in presence of this A only. So this A will be your left context. That's it. Okay, so here we do not have any right context, or roughly you can say right context is null. Similarly, I can say AB implies, say, A, B, C, B. If I say like this, then what will you say? I will say that A is changed to this ABC in presence of this B. So here B is right context. See carefully. I'm not saying that we should have only one symbol. We can have collection of symbols also. So here we have ABC. Okay, here we were having capital A is changed to capital D. Here capital A is changed to small c in presence of this A and B. So context can be anything. Okay, so let me give you one more example. You will get more clarity. See, if I say AAB implies AABCDEB, like this. Then what will you say? Here A is your left context, B is your right context, and A is changed to this entire thing. Okay, so I hope I have made the point clear. So A is left context and B is right context. Okay, please remember all these things. Let me give you one more example. If I say AAB implies AB, then what will you say? That here A is left context and B is right context and A is changed to null. Can I say like this? No, we cannot say, because this is not type 1. This is type 0, because here length is 3 and here length is 2. Okay, so please remember this thing. Here length is 3 and here length is 2. So this is not even type 1. So please remember that gamma cannot be null. Okay, so gamma cannot be null. It can't be null. It can't be null. Okay, because then it will be converted to type 0. Okay, I hope I have made the point clear to all of you. So please note it down, all these things. And let me give you one more thing, that null productions are not allowed in type 1. Are these null productions allowed in type 0? Yes, obviously these are allowed in type 0, but these are allowed in type 0. Please note it down, but these are allowed in type 0. Allowed in type 0. Why these are allowed in type 0? Because in type 0 we do not have any restriction. We are just saying that LHS must contain at least one non-terminal, and here we have at least one non-terminal. That's it. We are not concerned with anything else. Okay, so hence these are allowed in type 0. Okay, so please note it down. Let me do everything. Let me put everything on one slide, or you can say one screen, then you can note it down easily. Okay, so try to note it down if you are able to do it, or let me do it more shorter. Yeah, now I think it's perfectly visible on one slide. Please note down all these things. Now I'm jumping to next slide. Next is type 2. Type 2 is also known as context-free grammars. So again, we will have two conditions. The first condition is it must be type 1. Okay, obviously I have already said you all these things. And second condition is LHS implies RHS now. So LHS must be exactly one non-terminal and no terminal. Okay, exactly one non-terminal, and we cannot have any extra thing. Only one non-terminal is allowed, and RHS can be anything. Please try to remember this thing. RHS can be anything. So let me give you some example. If I say AA implies ABCD, is this type 2? No, this is not type 2. Why? Because LHS exactly one non-terminal. How we are writing this A? So this A must not be present now. How we are writing this small a? So this is not type 2. Okay, if I write A implies ABCD, yes, this is type 2. If I write A implies AB, this is type 2. If I write A implies AABCD, this is type 2. A or I'm writing again A and A. I'm writing again A. So let me write it S type. Okay. So we can have any non-terminal. This is obvious thing. I hope. Okay. So S goes to A, B, C, D, dot, 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 anything you can have. Okay. Now comes the important part. What about this thing? A implies null. See the definition. Exactly one non-terminal and no terminal. Okay, so we have exactly one non-terminal here, exactly one non-terminal, we have exactly one terminal. Right hand side, anything. So null is anything means what? We can have anything. So we can have null also. So A implies null is allowed. This is an exception. Please try to remember this thing. A implies null is allowed in type 2, but it is not allowed in type 1. It is not allowed in type 1. I have already said that null productions are not allowed in type 1, but these are allowed in type 0, and null productions are also allowed in type 2 also. So this is an exception. You have to remember this thing. And why this is an exception, or why we are allowing this thing? Because we have algorithm which can remove all the null productions from the type 2 grammar. Okay, so I will show you that algorithm after few lectures. So please try to remember this thing. Rather, in the chapter 2 itself, I will show you. Sorry, in chapter 3, that is PDA and contextual grammar. In that chapter, I will show you the algorithm, and we can remove all the null productions from the given grammar. Okay, hence please try to remember that null productions are not allowed in type 1, but these are allowed in type 2. Okay, why? Because we have algorithm to remove all these things. Okay, so this is why this is an exception, because in type 1 these null productions are not allowed, but in type 2 these are allowed. So this point violates now that it must be in type 1. So this is not in type 1. So how this can be in type 2? Because we have algorithm which can remove all null productions from the given grammar, or you can say from the given type 2 grammar. Okay, so hence this is allowed. So please remember this fact. Okay, so I hope I have made the point clear. This is all about type 2. Now the next is type 3 or regular grammar. See, regular grammar is also very simple. Regular grammar, again two conditions. It must be in type 2, and second is this is obvious now. Type 3 means what? It should be in type 2, and LHS implies RHS now. So LHS exactly one non-terminal, just like type 2. Here also exactly one non-terminal, but in type 2 we do not have any restriction on RHS now. We can have anything in RHS, but here we have restriction. That means T star n or NT star, but not both. So I will explain this thing in proper detail. So T star n means what? You can have any number of terminals followed by exactly one non-terminal, or exactly one non-terminal followed by any number of terminals, but we cannot have both in the same grammar itself. Okay, let me give you some examples. You will get a proper idea. Okay, so let us say S implies double A, triple AS. Is this type 3? Yes, this is type 3. Why? Because LHS exactly one non-terminal, right hand side, any number of terminal followed by one non-terminal. Okay, now T star na, to T star means what? Null is also allowed. So I can say S implies A. This is also type 3. Okay, because we have not kept any terminal. No problem. We are having one non-terminal. Okay, and let me add one more condition to this thing also, or T star. Okay, so RHS can be T star or this thing. Okay, so let me explain it properly. So S implies triple A, S, this is type 3. S implies capital A, this is type 3. S implies small a, this is also type 3 because of T star part. Okay, and S implies say A, B, C, D, this is type 3. Yes, S implies null, this is also type 3. A implies null, this is also type 3. Okay, because these are why? Just because, see, please do not say that null is a terminal symbol. No, null is not a terminal symbol. I have already told you many times. Just because of T star we can have null here. Okay, T star means what? Any number of terminals. So any number of terminals means what? We can have zero number of terminals also, and null represents zero number of terminals. Okay, I hope I have made the point clear. So all these productions are, you can say, allowed in these are according to type 3. Okay, which productions are not according to type 3? Let me give you some examples. Say if I write S implies ASB, this is not type 3. Why? Because non-terminal can be present either in the extreme left or in the extreme right. See here, either in the extreme right or in the extreme left. Okay, we cannot have in between. So here we have non-terminal in between these two terminals. This is not allowed in type 3. Okay, I hope I have made the point clear to all of you. And let me give you one more example. If I say S implies, say A, is this according to type 3? No. Why? Because we can have at most one non-terminal, and that too in the extreme right or in the extreme left. But we are here we are having two non-terminals. So this is not according to type 3. Okay. So type 3, see, if I write properly, then type 3 will be like this. Okay. T star, T star, or T star n. This is the first possibility for the RHS. Okay, for the RHS we are saying. LHS exactly one non-terminal, that is just like your type 2. And the second condition is, or you can say second way is T star or NT star. Okay, but and these two cannot be both must not be allowed in any grammar. Okay, so let me give you some example. See, if I write S implies AS or A implies AA or A. Now see carefully. LHS only one non-terminal, no problem. RHS only exactly one non-terminal, and that is in the extreme right. Here also in the extreme right, so no problem. For A, see on only this production. See, forget about this thing. See here, A, that means LHS exactly one non-terminal, RHS exactly one non-terminal, and that too in the extreme left. And here we have no non-terminal, that is also allowed because T star, because of T star. Okay, so now if we see individual production rule, all these are in type 3. But if we collectively say that what about this grammar, you will say this is not type 3. This is not type 3 grammar. Why? Because we have mixed these 2 points. Okay, so this I have written according to this point, and this I have written according to this point, but we cannot mix both. So that's why I have written but not both. Okay, I hope I have made the point clear to all of you. So this is all about type 3 or regular grammars. Okay, one more point I think I forgot, so sorry for that. For type 1, we said null productions are not allowed, but we have one exception to this rule also. That means null productions, only one null production is allowed in type 1, that is S implies null. See, if we do not apply, if we do not you can say give S implies null, or we do not allow S implies null, then null string cannot be generated by any grammar which is type 1. Okay, so type 1 grammar cannot generate null string, which is wrong, which is conceptually wrong. So we should allow this thing. So hence S implies null is allowed in type 1, but we have to make sure that S must not appear in RHS of any production rule. So S implies null is allowed. So no null production. See, I am repeating again, null productions are not allowed in type 1, but there is only one exception, that is S implies null. S implies null is allowed, but with restriction is allowed, but with restriction that S must not appear, S must not appear, let me write it properly, S must not appear in RHS of any production rule. In RHS of any production rule. Okay, so for example, if you say, see, if you say S implies, okay, let me show you one example. If you say S implies A, B or null, and A goes to AS like this. So what can you say about this? So is it type 1? No, this is not type 1. Why? Because S implies null is here now. S implies null is present, and S is present in RHS of any production rule. Hence, this is not type 1. Okay, please remember this fact. Okay, this is a very simplest example which I have shown to you. So here, see, S implies null is present, but I have said that S implies null is allowed in type 1, but with restriction that S must not appear in RHS of any production rule. But in this production rule, S is present in RHS, Hence, I will say that this is not type 5. Okay, I hope I have made the point clear to all of you. Okay, so type 3, I think you have already noted down. So this is again very important scenario. Okay, so please note it down carefully. Let me put everything on one slide so that you all can note it down. Okay, if you want more example on type 3, then I think these all things must be trivial for you. Na? If I say S implies say SAA or null, yes, this is type 3, no problem at all. Okay, now please do not say that S implies null is present and S is appearing on the RHS. No problem at all. In type 3, null productions are allowed. Okay, just like type 2, in type 3 also null productions are allowed. Okay, so I am writing here null productions are allowed. Null productions are allowed in type 3. In type 3 like type 2. Okay, see why this is allowed, because for type 2 grammars we have algorithm for removing null productions. Now since we have algorithm for type 2 and every type 3 is also type 2, so that algorithm will also run on type 3 also. Okay, so we can remove all null productions from type 3 grammar also. Okay, but obviously we cannot remove S implies null, because if we remove S implies null, then null string won't be generated by the grammar. Okay, so except S implies null, we can remove every null production from the grammar. Okay, and if we remove S implies null also, or you can say that null production also, then null string won't be generated by the grammar. Okay, so I will so please leave all these things. I will show all these things in the chapter 2, that is PDA and contextual grammar topic. Okay, when I will jump to that algorithm, I will show you each and everything. Forget about that things. Okay, so I hope I have made the point clear. So this is your what, type 3 grammar. Okay, so here we have the left na, and that is, this is according to point 1 or 2. This is according to point 1. Oh, sorry, point 2. This is according to point 2. Okay, similarly, if I say S implies say A S or AB, this is what, this is again type 3 according to point 1. See here, according to point 1, this is true. According to point 2, this is true. Okay, so see, you just have to remember one thing for type 3, that is there should be at most one non-terminal in the RHS, and that non-terminal should be either in the extreme left or in the extreme right, and these two conditions cannot be mingled up. That's it. So for type 3, just see LHS, there should be exactly one non-terminal, nothing more than that. In right hand side, there should be at most one non-terminal, and that non-terminal should be either in the extreme left or in the extreme right, and we cannot mingle up these two conditions. I hope I have made the point clear to all of you. Crystal, now I think this should be crystal clear to all of you. Okay, so I have repeated many times. If you are still not getting, then please rewind the video and watch it again. Okay, so I think now there is no need to give you more examples and so on. Okay, now let me tell you one more thing. Okay, so we have linear grammars. Linear grammars, see, this is now Chomsky hierarchy is over. I am just shifting to one more topic so that you get more clarity. Linear grammars. Linear grammars means what? LHS exactly one non-terminal, and RHS at most one non-terminal, and any number of terminals. So that means what? Since LHS is exactly one non-terminal, that means it should be type 2. Okay, so every linear grammar is type 2. Okay, linear grammar is, matlab every linear grammar is type 2. So linear grammar implies type 2. So I can say linear grammar, and this is your type 2. Okay. Okay. Now according to Chomsky hierarchy, we can make here type 1 and we can make here type 0. Okay. Now just tell me one more thing. Exactly one non-terminal is okay. What about RHS? At most one non-terminal. See here properly, we are saying at most one non-terminal and any number of terminals. So there is no restriction on terminal, but there is restriction on non-terminal. That means at most one non-terminal. That means what? Either no non-terminal, or if non-terminal is present, then it should be exactly one. We cannot have more than one non-terminal in the RHS. Okay, so let me give you some example. You will get more clarity. So let me say like this: S implies A. Is this production rule according to linear grammar? Yes, this is a production rule according to linear grammar. Why? Because LHS exactly one non-terminal, RHS at most one non-terminal. S implies A S B. Yes, this is also linear grammar. Why? Because see only one thing: LHS exactly one non-terminal, RHS at most one non-terminal, and we do not say about position now. We can have in the extreme right, in the extreme left, or in the middle, and so on. We can put it anywhere. So S implies S A B. This is also linear grammar. So now I hope I have made the point clear to all of you, and now you have already guessed it right. What about the relationship between type 3 and linear? So every type 3 will be linear, but every linear won't be type 3. Why? Because see this is linear, but it is not type 3. Why this is not type 3? Because type 3 is saying at most one non-terminal and any number of non-terminal. This is the same thing in the type 3, but we have one more restriction, that this non-terminal should be either in the extreme left or in the extreme right. We cannot have that non-terminal in the middle. But linear grammar, we are not saying about the position of this non-terminal. See here, see the previous slide. What we have said, that non-terminal is in either extreme right or in the extreme left. Okay, but here, and we are saying that any number of terminals. We are not concerned with terminals. We are concerned with non-terminal, and that non-terminal, there should be at most one non-terminal. Okay, but that non-terminal should be in the extreme right or in the extreme left. But here, what we are saying, we are not saying about position. Okay, I hope I have made the point clear. I have repeated many times. Okay, so now type 3 will be here. Type 3 will be here. Okay, so please, so you can say that this is modified Chomsky hierarchy form. Okay, so type 3, and then we have linear grammar, then type 2, then type 1, and then type 0. So every type 3 is a linear grammar, but every linear grammar is not type 3. You have guessed it right by now. Okay, so let me move to next slide. This is very important diagram. You have to remember this properly. For type 3 grammars, see, type 3 grammar generate, G means generate, regular languages. Hence, we call type 3 grammar as regular grammars. You see the previous slide, I have already told type 3 means regular grammar. So why we are calling them as regular grammar? Because they generate regular languages. What are regular languages? You will come to know about all these things in subsequent lectures. So type 3 means what? See, if the grammar is type 3, then it will generate a regular language. That's it. Okay, so a language is regular if and only if it can be generated by any type 3 grammar, or there is just a type 3 grammar generating it. Then we will say that language is regular. Okay, now so that regular language will be generated by type 3 grammar, and it will be accepted by finite automata, that is your NFA, DFA, etc. Okay, now type 2 grammar generate a class of language that is known as CFL, or context-free languages, and context-free languages are accepted by PDA, or you can say push-down automata. Okay, type 1 grammars. Type 1 grammar generate context-sensitive languages, and context-sensitive languages are accepted by linear bounded automata. And type 0 grammars generate recursive enumerable languages. REL means recursive enumerable languages, and these are accepted by Turing machines. Okay, so please try to remember this chart. I have spent sufficient amount of time so that you can learn all these things properly. Okay, so a language is said to be regular if and only if there exists type 3 grammar generating it. Please note it down, all these things. Please note it down so that you can remember. Otherwise, you will forget everything. So if anyone say define regular language, so you will say that regular languages, a language is said to be regular if and only if there exists type 3 grammar generating it, or you can say there exists finite automata accepting it. Similarly, a language is said to be CFL if and only if there exists type 2 grammar generating it, or there exists PDA accepting it. Similarly, a language is said to be context sensitive if and only if there exists type 1 grammar generating it, or there exists LB accepting it. A language is said to be recursive enumerable if and only if there exists type 0 grammar generating it, or there exists Turing machine accepting it. Okay, I hope I have made the point clear. This is the very basic point, and most of the competitive exam ask these type of questions. Okay, so this is the summary of your Chomsky hierarchy. Please try to remember these things. Okay, now let's move to the next slide. That is the construction of grammars. So Construction of grammars. In construction of grammars, we will first study construction of regular grammars, then slowly we will jump to context free, then context sensitive, and so on. Okay, now construct a regular grammar. We generate all possible strings over a and b. So how to construct this regular grammar? Since this is your first question, so let me introduce you some basic facts. See, we will write, see, if I write s implies as, by now you have guessed that s implies as means what? We can produce any number of a's. Now any number of a's can be produced, and we want to produce b's also, so we will write bs. So s implies as, bs means what? We can make any number of a's, any number of b's, and so on. Now for to, you can say, stopper means what? uh, uh, when we want to get out of this loop, we have an infinite loop now for a's and b's. So if we want to go out of this loop, or you can say stopper will be null. Okay, so this is the standard grammar which can generate all possible strings over a and b. So if you want to check, then you can check it out. Language generated by this grammar will be what? Smallest possible string will be null, because s implies null is present, so smallest possible string will be null. Now next string will be a. Why it will be a? Because you can write s implies as, and this s can go to null. So next will be a. Next will be b. Why b? Because s implies bs, and s can go to null, so we can have b. Then we can have double a b, ba, bb, dot. All possible strings over a and b will be generated by this grammar. If you want to check, say if I write like this, so is this string generated? Yes, obviously this string will be generated. See, first symbol is a now, so you will write s implies as. Now second is b, so you will make it as bs. Now next is a, so you will make it as as. Next is b, so you will make it as bs, and so on. I hope I have made the point clear. So please, here you can derive the string yourself also. So you just name the string, I can generate it with the help of this grammar. So it will generate all possible strings over a and b. Okay, now let's move to next slide. So now you should note this fact that s implies as, bs. This is your building block. That means what? Anything over a and b can be generated by s implies as, bs. Okay, now let's move here. Ends with a. Ends with a is again very simple. So we will write s implies as, bs. We can generate anything, and then stopper will be what? A. See, if stopper is a, that means what? Smallest possible string, lg, language generated by the grammar, smallest possible string will be a, because s implies a. Now next possible string will be what? If you write s implies as, now this s will be replaced with a, so we will have double a. Or you can have s implies bs, and this s is replaced by a, you can have ba. Dot. I hope I have made the point clear. So you can generate anything, any string over a, b, and then for, you can say, for removing s or for stopping s, we will apply a here. Okay, so I hope I have made the point clear to all of you. Now next is ends with double a. Again very simple. Again same thing, s implies as, bs. Now you have got anything. Now for, you can say, stopping s, we will write double a. So that means what? Double a. So side by side, please check that is it type 3 or not. Yes, obviously this is type 3. So in this production rule, we have one non-terminal, that to the extreme right. Here also extreme right, and here we have no non-terminal. That is again, obviously this is allowed. So I think this is according to type 0.1 na, cc 0.1. See the 0.1. Yes, this is according to type 0.1. Okay, see here. Okay, so according to 0.1. According to 0.2 also, that means left linear also we can write. Okay, so I think I forgot one word. See, this is what grammar is. You can say non-terminal in the extreme right now, so this is right linear, and here non-terminal in the extreme left now, so this is left linear. So type 3 grammar is either left linear or right linear. Okay, I hope I have made the point clear. Linear means what? Linear means the growth is linear. That's why we're calling it as linear. If we have two non-terminals, then that can give us exponential growth. 2 can give 4, 4 can give 8, 8 can give 16, and so on. Okay, so like this now. Okay, let me Let me show you properly why we are calling it as linear grammar. This is not required, but I'm telling you so that you get a good idea. See, if I write S implies SS, okay, or you can say we have two non-terminal in the right hand side, so we can have exponential growth. So 2 can produce 4, 4 can produce 16, and so on. See, S implies SS, we get 2s. Now these 2s can generate again 2s, so we have 4s. Now these 4s again generate, each is producing 2s now, so we can have 8s, and so on. So growth is exponential. Now if I say a, so all these will produce a. Okay, so I hope I have made the point clear that it will give us exponential growth. But if we have at most one non-terminal, or you can say as, then we will have only linear growth. S implies as, then as, then as, and so on. Okay, we cannot have exponential growth. We will have linear growth only. That's why we are calling them as linear grammar. So regular grammar can be either left linear or right linear. This is right linear, this is left linear style. Why this is right linear? Because growth is in the right hand side. See here, see here, S implies as. See, let me write it again for you. As, now this will give us as, so we will have double as. Now again it will have as, so triple as, and so on. So number of a's are increasing like this. So this is right linear. Okay, right side growth now. And what about this case? S implies SA. So I will say that S implies SA, then again SA. Okay, now this S is again replaced by SA, and so on. So here, what about the growth? Growth is from right to left now. So hence this is left linear. Okay, so type 3 grammar can be either left linear or right linear, but it cannot be both. Obviously it cannot be both, because we cannot mingle up these 2 points. Okay, so this is right linear and this is left linear. Okay, I hope I have made point clear to all of you. Now let's move to the current slide. Okay, see. So yeah, so here, so S implies AS, BS, or double A. So this is ending with double A. Okay, now let me write it again in another format. I can write like this also. S implies AS, BS, or A, and A goes to A. Okay, I hope you by now you have guessed that these two are equivalent grammars. So grammars are equivalent if and only if their language generated is same. Okay, grammars are equivalent if and only if their language generated is same, and I hope that you have guessed it right, that these two are equivalent, because we are writing here double A. So in place of double A, I have written A, and this A goes to A. Okay, and let me tell you one more thing. See, to generate any language, we can have infinite regular grammar. We cannot say 1, 2, 3 method, 4 method. We can have infinite regular grammars which can generate a particular regular language. Let me give you one more example. See here, we have written what? All possible strings over A and B. This was the grammar now. So I can write it like this also. If I write S implies AS, BS, null, this was the grammar. If I write one more production, double AS, double BS, so do you think that this grammar will generate some extra string? Please tell me this thing. Pause the video and try to think about it. Are these two grammar equivalent or not? 100% these two are equivalent. You cannot say that these two extra production rule will generate some extra string, because I have already said all possible strings over A and B can be generated by this grammar. All possible strings. If all possible strings are already generated, then how you can generate more extra, some more strings? Okay, so this won't increase any power. If you want to a simple proof, then I can easily say, see, S implies AS, you write like this, S implies AS. Okay, now again you write S implies AS. So what you get? S implies double AS, S implies double AS, and here this production is what? S implies double AS itself. So what is the benefit of double AS? So a double AS can be generated by AS also by just applying 2 times. So you apply this 2 times or you apply this 1 time, these are one and the same thing. Okay, so why you have written this thing? So you can delete this. So I have said that this is not increasing any, you can say double AS is not putting more strings, or you can say double AS is not generating some extra strings. Similarly, you can check for double BS also. So I have written 2 production rule with this grammar. Okay, and these 2 are equivalent. Similarly, you can write anything. Nah? If I write S implies AS, BS, or null, or A or B, okay, like this also, this is also equivalent to this. You can write anything, okay, whatever thing you want. So if I write S implies AS, okay, let me write it properly, AS, BS, null, then A goes to A, B goes to A, S, and so on. You can write anything, whatever thing you want. I will say with guarantee that everything will be equivalent to this only. Okay, so by now you have got an intuitive idea that for any particular language I can write any number of regular grammars for this language. See, for this language, or all possible strings over A and B, this is a regular language. Why this is a regular language? Because I am able to write a regular grammar generating it, and that is the regular grammar. And if you are able to write one regular grammar, then we can add any number of production rule and so on to it, and still that grammar will obviously generate the same language, but we have to write the production rule carefully. Okay, let me give you one more example, then you will get the idea. But the main idea here is that what I want to convey is that you can write infinite regular grammar for any particular regular language. For any particular regular language, we can write infinite regular grammars. Please note down this fact properly. Okay, now it ends with A. Now we have written this grammar. Now my question is, since in the previous in the previous question we have said properly that we can write any number of production rule, we can write any number of extra production rule. Now is it possible here also that we can write any number of extra production rule here also? See carefully. This is the regular grammar. Now if I write S implies AS, BS, or A, now I write one more production S implies null. Now tell me one thing, that are these two equivalent? No, these two are not equivalent, because this grammar can generate null string, but null string is absent here. Why null string is not generated? Because it is not ending with A. That's why. For ending with A, I have written this grammar, but for ending with A, this grammar is not perfect. Why this grammar is not perfect? Because it is generating null, but here with ends with A, null string is absent. Okay, so please try to remember, if you are writing any grammar for a language, then that grammar should generate exactly that language. We cannot generate extra string from that grammar, and we cannot say that the given string is in the language but it is not generated by the grammar. Okay, please try to remember these two things. See, this grammar is generating some extra strings. If this is generating some extra strings, then this grammar is not, you cannot say that this grammar is generating all possible strings over A and B, which or this grammar is for the language in which we have all possible strings over A and B which ends with A. Okay, so I just want to convey you a small message, that is, you cannot generate less strings, you cannot generate more strings. You have to generate exactly those strings only. You have to generate exactly strings in the language only. Exactly strings in the language. Exactly strings in the language. Okay, so this grammar is not for this language. Why this grammar is not for this language? Because this grammar is generating extra string, that is null. Null is not in this language, hence this grammar is not valid for this language. Okay, I hope I have made the point clear. So these two are not equivalent grammars. Okay, now if I write like this, S implies AS, BS, or double AS, or A. Now tell me that these two grammars are equivalent. Yes, 100% these are equivalent, because AS can generate double AS. I have already told you in the previous slide itself. Okay, so these two are equivalent, no problem in that. Okay, so again I want to say this thing, that for ends with A also I can generate infinite regular grammars. Okay, and while generating those infinite regular grammar, you have to keep in mind that all these grammars must be equivalent. Okay, so like this is not equivalent to this. Okay, I hope I have made the point clear to all of you. Now if you are not able to follow all these things, don't worry. If slowly you will get maturity, and after few lectures you will be able to solve each and every question. This is my guarantee. Okay, so just try to focus here. Okay, so this is all about ends with A. Now let's move to the next slide. Ends with double A. See, ends with double A I have already shown. Can you show me some other method for ends with double A? Yes, I can have obviously lots and lots of grammars. No, see, I can write like this also. S implies AS, BS, double BS, double AS, or double A. Okay, obviously AS two times can produce double AS, BS two times can generate double BS, and double A is present. No problem at all. Okay, so this is homework for you. So just try to play with all these things. This should be a toy for you. Try to you can say play with all these things. Okay, similarly here also I can write double AS, double BS, and so on. Okay, please try to focus. Okay, now let me give you one more question. I hope you will be able to solve it. AS, BS, double A, and A goes to A. Are these two grammars equivalent? No, these two are not equivalent, because smallest possible string, see the smallest possible string here, S implies double A, and A goes to A. Smallest possible string is triple A. We are not able to generate double A here. Okay, but ends with double A contain double A as a string. Okay, so ends with double A language will have a double A as a string, but here double A is not generated. So this grammar is not for this language. Okay, this grammar is not for this language. So I can say that this is the less category part. Why this is less category part? Because there are lots and lots of string in this language which are not generated by this grammar. Okay, and in the previous slide this was the more category now, because this grammar is generating more number of strings which were not ending with A. In fact, this is what I hope you have guessed it right. This is what all possible strings over A and B. Okay, so because of null, AS, BS null means what? All possible strings over A and B, and this A is extra part. Okay, so this is the more part, and this is the less part. So this grammar is generating less number of strings. Hence, this grammar is generating less number of strings. Hence, this grammar is not for this language. This grammar is generating more number of strings, and this grammar is not for this language. Okay, I hope I have made the point clear to all of you. Okay, so now I think this is more than sufficient. Next is start with A and ends with A. This is again very, very simple. See, I will say start with A means what? S implies AA. Okay, now on jumping to C, starts with A and ends with A means what? A, then we can have anything, and then we should have A. Okay, A, and in between we can have anything. So we are at non-terminal A now, and on this non-terminal we will write like this, AA or BA, so that we can generate anything, and then stopper will be small a itself. Okay, so this is the grammar, but there is only one problem, that single A. See, in this language starts with A and ends with A. The smallest possible string will be single A, because this single A is starting with A as well as ending with A. But single A is not generated by this grammar, so you have to write explicitly single A. Now this grammar is perfect for this language. Okay, I hope I have made the point clear to all of you. This is very, very simple. If you are still not able to get this thing, then please try to rewind the video and watch it again. Okay, so start with A and end with A. Okay, now let's move to next slide. double as substring. Again, very simple. Double as substring means what? Double as substring, starting and start. In start we can have anything, in end we can have anything, but in the middle we should have double A. So this is again very simple. In start we can have anything. Anything means what? AS, BS. Now we have generated anything. Now we want double A. For double A, you can write AA and A goes to AB. So for with this thing, see, from S we should write whenever we want to move out of S. Whenever we want to move out of S loop, then we should write this production AA. Now on A we should write AB. So now here we have double A. Okay, now on B we can have anything. Anything means what? AB or BB. Okay, but please write null also. If you do not write null, then language, you know what will be the language generated by this grammar? This grammar will generate language that is empty or phi. Why? Because nothing, no non-terminal is terminating. No non-terminating means what? See, S implies AS. You can write AS, BS, AS, BS, anything you can write. Any number of functions we can use. Now AA, then AB. Now this again this. So B goes to AB or BB. So how you will get rid of B? We do not have any idea how we will get rid of B. So hence we have to terminate this B now. So for terminating this B, you should write null. Okay. Now the language accepted will be your given language generated by this grammar will be in the given question itself. Okay. So this grammar will generate all possible strings over A and B, in which double A as substring. Okay, please you should note down the terminology. Grammar is a generating device, FA is an accepting device. So you should say properly that this grammar is generating all those strings over A and B, in which we have double A substring. We should not say that this grammar is accepting all those strings over A, B, in which double A substring and so on. Please do not say these vague words. Acceptor is finite automata. That means FA is used to accept the regular language, and this grammar is used to generate the regular languages. So regular grammar is used to generate the regular languages, and FA is used to accept the regular languages. Okay, so I can write, you should write all these things. Regular grammar is used to generate regular languages, and FA is used to accept regular languages. FA is used to accept regular languages. Okay, regular grammar is used to generate regular languages, and FA is used to accept the regular languages. So please note it down these points carefully. You will get confused after a few lectures. You will get confused in all these points. Okay, so please use the terminology properly. Regular grammar is used to generate the regular language. And again, I am saying this again and again. Please note it down properly. A language is said to be regular. See, I am saying that double A substring. This language is regular. Why I am saying it is regular? Because I am able to generate a regular grammar, or I am able to write a regular grammar which can generate this language. So language is said to be regular if and only if IFF. That means both ways. A language is said to be regular if and only if we are able to write a regular grammar generating it, or we are able to write FA accepting it. Okay, so for double A something, I have already written FA for you. I have already designed FA. You can see my previous lectures, and in this lecture I have given you idea about regular grammar, how to generate a regular grammar for double A substring. Okay, I hope I have made the point clear to all of you. Now and see, this is not the only way. There are lots and lots of ways. This is your homework, so try to generate a regular grammar yourself, but that regular grammar should be different from this grammar. Okay, because I have already said that for a regular language we can have infinite regular grammars generating it. Okay, now let's move to next slide. This is again a good question. Number of A's are divisible by 3. Number of A's are divisible by 3. How to write a regular grammar for it? See, this is a very simple task. We will say S implies, see, do not say S implies AS. If you say S implies AS, then we cannot have record of number of A's. We can apply this production rule any number of times, and we can generate any number of A's. Okay, so but we need number of A's should be divisible by 3. So do not write S implies AS. So what should be written? We will write S implies A. We will move to a non-terminal A. Now A, we will move to a non-terminal B, and on B, we will move to non-terminal S. So now see, S implies A, B, AS. So we have a loop type, na? So A like this. See, you can visualize it just like your FA. S, A, B. Number of A's are divisible by 3. You remember the FA? If you are not able to remember, please see my previous lecture. And A like this. Okay. So S implies A implies A, B implies AS like this. Okay. So now number of A's should be divisible by 3 now. So we should write null here. This should be your final state now. Initial should be your final. And why this should be final? Because if we have not read any number any A, and still we are at final state, that means string must be accepted. That means null string has number of A's divisible by 3, because null string has 0 number of A's and 0 is divisible by 3. So null should be accepted, hence initial should be final. And so on. I have already said you all these things in construction of FA part. You can watch these lectures, watch those lectures. Okay, so S implies null. Why we are writing S implies null? Because number of A's should be divisible by 3, and null has number of A's divisible by 3 only. Okay, what about my B's? What about my B's? I think you should remember we have a self loop of B now. So we will write here BS, BA, and BB. Okay, I hope I have made the point clear. So this is regular grammar which generate all possible strings over A and B in which number of A's are divisible by 3. Okay, so this is very simple grammar. You should note it down. Now if I say remainder one means what? This should be the final state. Okay, so if I say remainder 1, then this should be the final. This should be the final. So final means what? Final should be null terminating. Okay, so in place of writing null here, you should write null here. If I say remainder 2, I think you should remember now. This is remainder 0, remainder 1, remainder 2. I am repeating again and again. If you are not able to follow all these things, then please watch my construction of FA lectures. You will get the idea. So, see previous few lectures. Okay, so remainder 1 here null, remainder 2 here null. Okay, and if I say not divisible by 3, that means what? Remainder 1 or remainder 2. So you will write both null here. So let me show you properly. So let me do it this way. Please first note it down. Note it down these things. Note it down these things. Now I say remainder 1. Remainder 1 means what? This will be the final. Okay, this won't remain final. This won't be the final. Okay, so okay, this will be the final now. So I will remove null from here, and I will write null here. Now if I say remainder 2 means what? I will make this as final. So final means what? Null terminating. So remove null from here and apply null here. If I say not divisible by 3, that means what? These two will be final. So this will be null. I hope I have made the point clear. Now this should be just like a toy for you. Just try to play with this. Okay, just try to generate strings and so on. You will get the idea. Okay, now let's move to next slide. So please pause the video and note it down carefully. I am moving to next slide. Okay, number of A's and number of B's are even. So I hope you have made FA for this. In the previous lectures, I have show you how to construct FA for it. So similar idea I will apply here for your construction of grammar. See, we cannot write grammar directly. We first have to write DFA. Only then I can convert it into grammar, because it will be very tough. Okay, so let me say it this way. We will have a start symbol as A, B, and C. This will be your initial as well as final, because null has number of A's and number of B's as even. So you remember na grid automata? A, B, sorry, B and B. Okay, I hope you remember all these things. So number of A's and number of B's are even, huh? So your S will be final. So just write your you can say grammar. S implies small a, capital A, small b, capital C. Okay, now capital A implies small a S or small b B. Capital B implies small a capital C or small b capital A, and capital C implies small b capital S, small a capital B. Please note it down carefully. S implies A, see here A, and B C. B is going to C. A implies AS and B B. B implies AC or BA. C implies BS or AB. Okay, so now everything is fit and fine, but still the language generated will be empty language because I have not terminated even a single non-terminal. So we should terminate it. So final is S now. So in place of final, you will write null. So now this S will be terminated. Okay, so I hope I have made the point clear. So so this is the shortcut. Now if you are not able to guess the regular grammar, then first construct FA and then convert that FA into regular grammar, and the step you have already noted down, that the final will be null terminating and so on. Okay, now next is construction of context-free grammar. So this topic I will start the next lecture from this topic itself, because I hope 1 hour is already over. Okay, so in this lecture, just to give you a summary, I have shown you properly about Chomsky hierarchy. Okay, Chomsky hierarchy I have shown you type 0, type 1, type 2, type 3. Chomsky hierarchy, then I have given you definition of type 0, then type 1. Okay, type 1, then type 2. Okay, then type 3. Okay, then I have shown you something about linear grammars. Okay, and the relationship with the Chomsky hierarchy and linear grammar. So between 3 and 2, between type 3 and type 2, we have linear grammars. Okay, and then I give you summary about your Chomsky hierarchy. And again, I am repeating, a language is regular if and only if there exists a type 3 grammar generating it, or there exists F accepting it. So this is the way. If you get a language in an exam and they say that is this language regular, then you just have to think about regular grammar. If you are able to think about regular grammar which can generate that language, then we will say that it is a regular language. Otherwise, we won't say that it is a regular language. And of course, there are some shortcuts. I will show you all these shortcuts in the upcoming lectures itself. Okay, so don't worry about them. So by now, you should have an idea that is the given language regular. How will you show that this language is regular, or how will you prove that this language is regular? Just try to write a regular grammar generating it, or try to write an FA accepting it. Any one way will be okay for you, because if you have an FA, obviously you can convert it into regular grammar, and if you have a regular grammar, then obviously you can convert it into FA. I have already shown you this thing in this lecture itself. Okay, so now next topic we have started, that is construction of grammar. And the first was regular grammar construction. I have shown you many examples for regular grammar construction. Okay, and in this lecture itself, we have concluded the regular grammar construction. In the next lecture, we will start with construction of context-free grammars. Okay, thank you so much. Bye bye.